His work has appeared in the New York Times, the New Yorker, Bloomberg, Financial Times. I feel pretty confident saying that if you have read the news in the past few years, you have likely read about his work. He works in so many cool applications. He has a bunch of cool awards, but I think I'm just going to let us get straight to his awesome talk and turn it over to Seth.
Thank you. Thank you so much for coming. How long do you want me to talk for? Questions? What's your standard?
I mean, I think since we started at 4:10, maybe try to end by 5, and then we'll do questions. Just give people a chance if they have to run, and then questions.
Questions at 5. Okay.
Right,
questions at the reception as well. But if you have clarifying questions in the middle, feel free to ask them. Yeah. Cool. Okay, so inferential artificial intelligence. I might have made up this term. I've been giving this talk to people who do public health, but today, really excited to be here. So I'm not going to spend too much time trying to tell you what AI is or tell you why it's really just applied stats, but I'm going to give you some cool case studies. I have 5 of them. Here are the 5 case studies. I'm going to do the last 2. So if you really are excited about the other ones, take a picture of those slides. You can go download them. But I'm going to tell you about deep generative modeling. I'm going to tell you about small area disaggregation. And okay, let me tell you what I mean by inferential artificial intelligence. So here we go. So you all know what machine learning is. This is from my professor. I did my PhD at Carnegie Mellon from Tom Mitchell, but you know what that is. Maybe you don't know what inference is. Inference for me is just drawing conclusions from data. Nothing more complicated than that. I'm not talking about philosophy and deductive and inductive and just, we have data, we want to learn things, we're going to draw conclusions from data somehow. We're going to do that using computational statistics, machine learning, artificial intelligence. So inferential artificial intelligence, for me, is using computational statistics and machine learning to draw conclusions from data. And so now I will tell you about 2 case studies where we do that and are doing that. And they're both in progress. So I would love to hear your feedback, your thoughts, your applications, your ideas, your comments, your criticism. So now I need to jump all the way to case study number 4, which I think I can do here. The tension is building, the suspense. Can I find it? I found it. Okay. So I do a lot of spatial statistics. I've done a lot of COVID work. This is COVID incidence. And there are these workhorse models in spatial statistics, like the conditional autoregressive model, which is just a multivariate Gaussian with a specific structured precision matrix that's sparse so that computation is tractable. That's all it is. That model, despite it being sparse, is still not very computationally tractable because it's a big matrix and you're still inverting it and it's sparse and it's hard to have your models mix and there are all sorts of other problems. So we have been thinking for a while about how we might speed that up. That's been a theme of my work for a while. And we have this cool new idea, which is to use variational autoencoders, something we call prior VAE, and we get these big speedups. So this is just the advertisement part, and then I'll tell you a little bit about how the method works. So if you're used to running MCMC, sometimes it takes a while. Sometimes it takes 300 seconds, 300 seconds, 277 seconds. And that's okay, maybe you're happy with that, but wouldn't it be nice if it only took 8 seconds? And even better, the effective sample size, the number of samples that you actually have, adjusting for autocorrelation, well, wouldn't it be nice if the effective sample size was an order of 10 more for a lot less time? And here, finally, we have the effective sample size per second, and we have this major speed up. So that's the type of speed up we're hoping for. And now I'll tell you a little bit about how this works. Here we go. So you've heard of variational autoencoders, probably. Here's a quick reminder. It usually has this bottleneck structure. That's not that important for us. It could be that our variational autoencoder doesn't do any compression, but to fix ideas, basic setup, what you can download a tutorial in 5 minutes in any deep learning framework, PyTorch, TensorFlow, you will have a setup that takes in as input pictures of cats or dogs, that's pretty standard, and tries to reconstruct them having encoded, and forget about the variational part for a second, vanilla autoencoder, decoded, and we get something that's sort of like a somewhat blurry or noisier version of the original image, yeah? So we train that with reconstruction loss, basically just mean squared error. And then the variational part, the way that I think about this, I don't give this like a real Bayesian interpretation. For me, this is just a regularizer on the samples here, because we would really like them to be normal, independent IID draws from normal 0, 1, normal 0, I. Yeah? And so the KL divergence that you're probably familiar with if you've ever seen this, for me, all that is a regularizer. And this is going to be super useful for us, not to generate pictures of cats, as much as we might want to do that, because we like looking at pictures of cats, but to generate draws from a prior that we're interested in, like a spatial surface. So here's a picture of a Gaussian process. I drew that. And it gets fed into the autoencoder, and then out comes, well, we should be able to pretty much perfectly reconstruct a simple function like that. Yeah? So the whole idea here is deep generative modeling, which includes variational autoencoders, GANs, diffusion models. Deep generative modeling works really well. People have been working on it too much, perhaps, because it's not clear why we need all these pictures of cats. Let's use all of that machinery for statistical inference. What is the problem that we often have? The models, we can write down really cool, interesting models. We can simulate from those models, but inference is very costly. Sometimes there's intractable normalization constants. Sometimes things are doubly intractable. Sometimes the parameters are, there's a lot of them, and they're all correlated. And so sampling is very, very difficult. It takes a while for chains to mix if we're using MCMC. Or maybe we're using variational inference, and we are not convinced that we've done a good job characterizing the uncertainty or even getting the right answer. So we have a new approach here. And so that's it. We plug in infinite data, right? Because the simulator is just draws from a GP or any class of functions, any surface of smooth Gaussians, or later on, anything else that you might come up with, simulations from an ODE for infectious disease. So we just take draws from some prior. What luxury to have a chalkboard. F is drawn from a GP. And we plug that into the autoencoder. You should already be thinking, autoencoders just takes in vectors, right? How are we going to deal with actual functions, infinite dimensional vectors? Get to that later. We take F, evaluate it at a fixed set of locations. That's how we deal with it in this simple architecture. Plug them into the encoder. Normalize things so that when we decode from a normal 0, I, we get things that look like what we plugged in. Okay, everyone with me? Feel free to ask questions now. And why is it infinite data? Because we just wrote down the data distribution. It's the prior that we think we want to use. Okay, having done that, we can now rip out this decoder and put it into an MCMC inference scheme, into a probabilistic programming language. And so here we go. This is some, not really pseudocode, this is real code in NumPyro, if you've never seen it before. I think it's pretty intuitive. We can put priors on parameters that we care about. So sigma is a parameter that we care about for the observation model in a GP. Are people familiar with these terms? I can go into more detail if you need them. So if y is data, y conditioned on f at a certain location, si, let's call that yi, is, let's say, it's normally distributed, centered at f of si, with some variance sigma squared. And so if f is the GP, the data looks like that, IID noise. Question, yeah?
Yeah, one small question to the previous slide. So do you enforce the distribution to be in a certain shape, sort of ensure continuity with a better variation autoencoder, or is it a simple autoencoder?
For us, choose any simple thing because we have infinite data. So we're happy to not enforce sparse smoothness, not enforce anything. If you want to think about the mathematical properties, by all means, make a choice that corresponds to the class that you have in mind. But this is a universal function approximator, and we can sample for days if we wanted to. So as long as it can express anything that we have in mind, we will let the model take care of matching that.
So you don't need a like an information gradient while you move in the space of the probability distributions you're learning, right?
No, we do not have to worry about anything like that. Maybe that would help. I would love to hear more about what you have in mind, but we do not do anything that complicated. Anyone else? Okay. so that's the beginning of the model is sigma has a prior. And this is what happens if we're just doing a Gaussian process. This is not with the VAE. So with the Gaussian process, if you have a fixed set of locations denoted here by x, and you have some covariance matrix parameterized by a kernel, so that's why we're calling it K, otherwise known as a Gram matrix, we get samples here, F, drawn from a multivariate normal distribution with mean 0 and that covariance matrix. And then that's the prior. Likelihood, Y is drawn, and it's exactly what I wrote down. Sorry, I forgot to get rid of, well, whatever. You might have a certain set of observations. I was trying to simplify things, but maybe you only observe this function at a few locations, so that goes into the observation index. And so this is a normal distribution with that mean and that standard deviation, and that's it, right? So no VAE. This is just to show you how you would do the model, but this is not going to sample very well, right? Because all of these F's are by design very correlated. F at this location is very similar to F at that location. And if you've done this before, you know that you can take a Cholesky decomposition, and there are other tricks to make this sample a little bit better, but it's still kind of a pain, and it doesn't scale very well. If we have 1,000 observations, it's 1,000 cubed computations to calculate that matrix. That's not written there, but these computations get very intractable. By contrast, here we go. We have written the decoder, a very simple decoder with a ReLU and a linear combination of weights and biases for some Z input. And then we've got that hidden layer, so nonlinearity on that hidden layer. And then we've got our output, which is another set of linear combinations. And that's it. Single layer, very simple decoder. OK, so this is what we trained already. We ran the process of training this for millions of observations. Now we fix that feed-forward neural network, that decoder. We have it here, and it is ready for us as a drop-in replacement where we say instead of sampling F directly from the true prior, we sample Z from normal 0I, because that's how VAEs work. That's how we generate from a VAE. And we plug that, did I say Z? Sorry, I am American. I've just been written for too long. We plug that Z into the decoder with those weights and biases, which are fixed. We're never learning those at this stage. And we get out F. And so this is an approximation to the true F that we would have gotten from here. But this makes everything sample much, much better. Maybe it's low dimensional. Maybe we can have some compression and make things smoother. But we don't need to. And then otherwise, things are the same. It's the exact same code here. We have the same likelihood. So this is a drop-in replacement for priors. That's why we call it prior VAE. There's similar work that other people have done in all sorts of ways with diffusion models, with neural processes, and they've always been, from my perspective, trying to do the whole problem at once. They're trying to use variational inference with this complicated neural network model in order to replace MCMC. But MCMC is great. MCMC works. Yeah? We know that it works. We can check for convergence. We know that the posteriors are what we want. It's just that sometimes sampling is slow. And so what we are replacing is the slow part of sampling. And we think, we have some evidence for some more complicated models that we can use this for things where otherwise you would need to resort to something really slow, like ABC, approximate Bayesian computation, which is like, yeah, not a good thing to be waiting for something to sample. OK, so questions about this drop-in replacement? I'll now do another advertisement for how fast it is, and then I'll tell you about the stochastic process version of it, which is very cool. Basic idea. You could go home and do this, yeah? You have some model that you don't really know how to turn, here we know how to do it. But maybe you're interested in something that seems very simple. Positively constrained, monotonically increasing GPs. How would you do that? It's not actually obvious, right? You could do it with rejection sampling, but it would not sample very well because what's the probability that you draw from a multivariate Gaussian and it's always increasing and positively constrained? Low, 0. OK, so that's fine, as long as you have some way of simulating. Yeah, question?
Yeah, so is there part of the pipeline to verify that your decoders match the prior?
So this is an area of active research. Currently, what we have is the loss function that I described, reconstruction loss, mean squared error. And what we see in practice is that it does a good job, but it's underestimating the variance of the true spread of the distribution of things that we care about. And so something that we are currently trying to figure out, but if you have thoughts, please let me know, is what is a better loss function? Wasserstein comes to mind, something that will tell us the whole distribution. Are we really capturing the tails, basically? Other questions? Okay, so here's what it looks like. These colors aren't really showing up that well. Here are draws from the prior. Here is exactly what we would like to see, concentration of the posterior when we put in 2 data points. 4 data points, things are really concentrating, 6 data points. And you can't see it very well, but there is ground truth, meaning, no, I don't think we're showing it here. We're just showing the VAE here, yeah, sorry, just trying to remember the example. Okay, so it does work. It does give you, on simple examples, the type of things you want. Here it is on a challenging spatial example, 60 different regions in Zimbabwe. We have estimates of HIV prevalence. And these are the types of spatial disease mapping problems that people fit all the time. And sometimes it takes on the order of, well, that's not that bad, 13 seconds. But you can imagine that if you're doing this over time, so it's not just those 60 regions, but 60 times 52 weeks. If you're doing this and you're continuously adapting your model, trying to figure out what the best model is, it can add up a lot. Actually, this is only 13 seconds, but that's not enough effective samples to say much about the uncertainty, right? So if you wanted 10 times as many, it would be 2 minutes. So again, a huge speed up, 70 times speed up. Yeah?
Seems like from the observation, both the car and the VAE car, like a blurry version of the...
Yeah, and that's right. That's what we're doing when we're doing spatial smoothing. I can talk a lot about small area estimation, but basically we've got our direct estimates in each of these districts. We believe we know from a survey what the HIV prevalence is, but those estimates are noisy. We want to stabilize them. And so this is like the right answer from the perspective of this stabilizes them by smoothing them out spatially. Whether that's actually the right answer depends on the application. And you might over-smooth, you might under-smooth, you might want to learn how much smoothing you should do. That will become possible if you have a nice tractable model. Cool. Okay, another example, another big speed up. This is the UK. So yeah, I think that I should now tell you about stochastic processes. Although the other question you might be wondering is, what about parameter inference, yeah? So length scales for GPs or other parameters that you might have in some complex model. How can we infer about those? So I'll do both of those. So that's to get you thinking. So stochastic processes, right? I sort of promised this is a GP, but really I've only done multivariate Gaussians where I've specified the set of locations in advance. And what about key parameters? How smooth should it be? Or which kernel should I use? So let's see what order I'm going to do these things. Here we go. So this is parameter inference. So there is a standard elaboration of the VAE called the conditional VAE, CVAE. And there's one tiny change here. We add a conditioning variable. I've never quite figured out why people like that terminology. I'm going to call it a hyperparameter of the model. So the length scale, how smooth it should be, something else that you might care about. And so that just comes along with the data. So I generate from a GP, mean 0, covariance k with some length scale lambda. Lambda has some prior gamma 1, 1. This is f conditional on lambda. And now I'm going to encode, along with those f's, I'm going to encode the actual value of lambda. That's the c. And that's information that I know. There's no reason to keep that a secret from the model. And that's information that the decoder should have access to as well. And if we put that in here and in here, we will learn a conditional encoder, a conditional decoder. And then at inference time, we can do the actual thing we care about. Sample from the prior, exactly as we wrote there. Lambda comes from a gamma prior. And put that lambda into the decoder so that we get the right prior out, conditioning on that variable. Okay, that's why it's called a conditional VAE, I suppose. So here's what the code looks like. I tried to simplify things a little bit. Here's that C variable, and it just gets concatenated with the random Zs. You could imagine a different architecture, but this works very, very well. It's just like what we showed here. It's just sticking it on there. And so for the decoder, sorry, sticking it on there. And that's the decoder. And then the model says, okay, in this case, it's not a gamma, but a uniform. I don't know why it's not 0, 1, but anyway, a uniform distribution on C, whatever C is. And then C gets passed into the decoder, and that gives us Fs. But in the posterior, we can now learn C. It's no longer a mystery what that C is. Yeah?
Sorry.
Yeah?
So for the C, is you concave the C with the original vector, but the dimension changed, so you change your G vector.
So the encoder concatenates it here.
Yeah.
And so then this encoder knows that C might be, if C is really short, it's really wiggly. If C is really long, it's really smooth. So the encoder has access to that information, and it puts that basically into a Z, a latent encoding. It's a little interesting exactly what's going on here. The way that I think about it is that, and I'll say this again and it becomes more clear in the full stochastic process way of thinking about things, the Z is like the randomness in the function draw. Yeah? So it's like, does it wiggle up or does it wiggle down? That's the Z, Z. Okay, I'll use British English. It's easier to hear what I'm saying. The Z is like, what, is it high and then low? Is it low and then high? The C is how quickly do things move? How wiggly is it? So C is, it's wiggling down here and then it's wiggling up here. And so those things get disentangled by the encoder so that we just have a Z. And if it's helpful, like, okay, this is used for digits, right? So you put in MNIST digits, a 1 goes in, and then a 1 comes out. But we tell it that it's 1. And then suddenly we get a decoder that we can ask, give me a set of really beautiful 1s, now give me a set of really beautiful 2s, now give me a set of really beautiful 3s. That's if it's categorical. If it's continuous, this is how people do like smoothly change from a 7 to an 8. And it would actually somehow learn how to do that. Yeah? But yeah, we do just concatenate, and that seems to work well. Again, we're sort of taking the simplest choice we can until something tells us that we need to do something more complicated. Okay, so that's it. It goes into the decoder, we get our F, we do our inference, we get a posterior. There is a Colab demo if you're interested. And here's what it looks like. So we do a really good job recovering the truth. So what's going on here with the colors? So orange is the GP. That's fit with HMC in NumPyro, and it takes a really long time to fit and has a terrible effective sample size. Prior VAE without conditioning is the fastest, but it does not do the best job with uncertainty. I'm not entirely sure that I can explain the intuition of that, but it ain't perfect. Prior CVAE, the new thing, comes a lot closer, although it's still not perfect. That is in blue, and so it's this mauve color. I don't even know what that is. And it's a little bit slower, but the posteriors are great. So there's this one parameter, B, the length scale, and here are the posteriors from prior CVAE and from the GP, and they match almost perfectly. You can see this nice concentration. This was the prior. This is the posterior. And we don't have a posterior for that parameter from prior VAE, the original approach, because everything was just mixed up. There was no way to learn that posterior. Yeah?
So you're showing the sample time improvement at inference time. Is how big of an issue is the training time required?
So this is a great question and perhaps a fair criticism. It just depends. It's not something that we've spent, because usually it trains pretty quickly, and we think of it as a one-off price to pay. We're doing work with practitioners in the UK, so we're going to spend a day getting a good prior, and then it's just going to be fixed, and then we're going to do inference really quickly. But you can imagine that there are settings in which you do really worry about that training cost and time. We're not worrying about that for now. Okay. Doing great on time, so I'm going to tell you about a different version of this called pi VAE instead of prior VAE. So what's special about stochastic processes? They're not random functions. Wait, that's wrong. They're not random variables. They're not random vectors. They're random functions, right? Yeah? Cool. So this is motivation. This is not truly how we derive things, but I think it's really nice motivation. So if you've never seen this before, this is the other KL not Kullback-Leibler, but Carhoon and Love. A centered stochastic process f of s can be written as an infinite sum.
Are you seeing something besides the link on yours? Because we're only seeing the link.
This is like what happens on Zoom, but in real life.
Great.
PyVA, here it is, stochastic processes. Thank you. Please tell me if I'm being nonsensical. Carhoon and Love, the other KL. A centered stochastic process, f of s, so think of a realization of a time series indexed by s, or a spatial surface, or anything more complicated, can be written as an infinite sum of basis functions. That's the phi j. J goes from 1 to infinity. Weighted by random, get American English right, betas, beta sub j from j equals 1 to infinity. Yeah? So maybe you've seen this, maybe you haven't. It's kind of cool that this is possible. We're going to take this idea and turn it into something we can learn with neural networks. So we're going to propose a novel variational autoencoder inspired architecture inspired by KL. So we do a couple different weird things, but this is the basic idea. We're going to learn phi, the basis functions with a neural network with a multilayer perceptron, and we're going to have those betas, which are random, come from a variational autoencoder. So I think I just said that. Phi has a deep neural network architecture, feature representation. What does it do? It encodes the similarity among input locations. So to give you some intuition, if it was a GP, it would be saying, how smooth is it, right? Because if the covariance is really high from here to here, then there can't be that much variation. If the covariance is really low from here to here, then it can wiggle a lot in between. So that's what phi does. And then beta gives us different random realizations of the function. So the beta j's are random. We're going to learn that with a VAE. OK, so we're going to do the same thing. We're going to have infinite training data. But now we're going to need to let things vary. We're going to need to look at different locations, S1 through SK, and that's going to be random. We could have different sizes of the sets that we train it on, because it's a function, so you can have an infinite set of locations, and you can pick whatever you want. To write down the for loops and to implement this, it is simpler to keep capital K, the number of observation locations, fixed. But there's no reason you have to, and I think it sort of depends on which deep learning framework you're using, how simple it is to code this up, or how annoying it is. It's a little annoying. And so, yeah, we've got the observation locations, Si1 through Sik for I equals 1 to capital N. N can be a million observations of these functions. Each function is different. It's a realization from that stochastic process. And then we've got yi1, so at that location Si for function number 1, what is the value? Yeah? OK, so the architecture's kind of a pain. I don't know how much you're going to get from this. Please read the paper and also read the code that makes it a little clearer maybe. But anyway, we've got that phi, and we're going to learn it. It's got weights and biases. That phi evaluated at some Sik, at some location, multiplied by some beta, the beta is going to come from somewhere, we're going to have to learn that beta, gives us the data, yeah? And so this is really written down here like the Carhoon and Love, a finite approximation to that. Question?
Yeah, so how's the relationship between the phi function here and, like, imagine you just concatenate several layers after the decoder. Like, seems like they're working in a similar fashion.
OK, so the decoder that you're thinking of from the previous set of slides, yeah, that was doing something very similar. But that was only for a fixed set of locations. And so we need to generalize here to say that phi can take any location. Yeah, previously it was random vectors. That was what we were encoding. Multivariate Gaussians at its fixed set of location, that's a GP, random vectors. And so phi was only taking, in fact, that phi was taking in Z, the random, yeah, they're different. I mean, it's weird because they're sort of doing the same thing, but this phi this is more like the Cholesky decomposition. Yeah, if you have a covariance matrix K for a Gaussian process and you want to sample from that Gaussian process, how do you actually do it? you take LL transpose equals K, covariance matrix, Gram matrix, and then you take Z from normal 0, I, and then you multiply LZ, and that gives you a sample F from a GP with that covariance matrix. Okay, so this phi is a nonlinear version of L. That's the way that I think about it. And the Z, well, the Z is the betas, but the betas, those come from a VAE to make it more nonlinear. And it's not clear that we need all of this nonlinearity. We could probably simplify this a little bit, but this is what we came up with. Seems to work pretty well. It's kind of a pain to tune. Future work, there's a PhD student who's just come. We're going to be simplifying things in various ways, trying to figure out what we really need. But this is the architecture we have now. So yeah, it's got a VAE in here. It's got that phi. And we look at mean squared error of trying to reconstruct things. But we do it twice because there's the beta that we learn from gradient descent. And then there's the reconstructed version of the beta from the variational autoencoder. And we have both of those losses in there. And we have the KL loss to regularize things. And yeah, it's got some cool properties. So let's talk about those. But any questions about the setup? OK, so cool properties. So it really is a stochastic process. And there's a proof of that, which isn't actually that deep because it's just taking Gaussians and doing some nonlinear things to them. So it is just, yeah, I think I have the proof on the next slide. But anyway, let me just tell you, if you've seen this before, it's nice to understand this notation, sigma script F script P, yeah? Show of hands, people who took stochastic, took measure theory classes. Okay, enough of you have been subjected to this that it's worth me saying it. So what happens? We've got a stochastic process X with samples omega from the sample space capital omega at locations S, an index set, space, time, yeah? So the pi VAE equivalent says that those omegas, the randomness, that goes with the betas, yeah? And so F is just defined to be this, beta transpose phi of S. And so if we were to fix a location, suddenly, for that fixed location S, X sub S of omega is a random variable, right? That's how stochastic processes work. And that's something we can transparently see from the pi VAE equivalent because we fix S, beta's random, and so this is a random variable. Yeah, cool. And what if we instead fix omega? We have one realization of this stochastic process. We have an entire sample path for that realization. We have a random function that we have observed. So S in S is a realization. So sorry, X sub S of omega for a given S, and S is a realization from a stochastic process. That is a function. And the pi VAE equivalent, so now I'm saying F for any location, because it's a function, is beta transpose phi of any location, right? Because we identified beta with omega from the sample space. So it can be evaluated at any S. Different betas give different realizations. Yeah? OK. And I guess this is the proof. I won't go through the proof. It's not the most exciting proof. In an early version of this, we had some stuff about Kolmogorov extension theorem. You don't need any of this. It's very simple, but I'm not going to go through it now. Look at the paper. OK. And it works really well. And I guess I'm going to go out of full screen here. I'm going to go back to PowerPoint. I'm going to go to full screen. I'm going to check that you're looking at an amazing picture of pi VAE on a very complex and difficult spatial reconstruction task. So these are 3 countries in East Africa. We have land surface temperature. The true data is here. Yeah? And we're going to take 6,000 randomly uniformly sampled points, and we're going to try to infer the land surface temperature. OK, so this is our pi VAE approach, which gives a very low mean squared error. This is supposedly a full rank GP, but I think, is David here? I think that there are computational difficulties with the package that we use such that maybe we shouldn't think of it really as a full rank GP, but it was the best thing that was out there in terms of how you can fit GPs to that scale of data, which isn't that large, 6,000. David has a new paper. I'm on this paper, which uses some inducing point methods and does pretty well, not as well as this one, but still better than these other things. And then in-law is sort of the state of the art for spatial statisticians, but not going to go into details unless you care. And we do much better than in-law, which is, you can see, it's too smooth, right? So there's lots of fine scale spatial variation. And what's really going on here? Like, what GP did we use? What is the prior? We did something weird. Yeah, we have PyVAE. It's got multiple layers with ReLUs. It is approximating with more capability a function class, which is, I believe, GP with a Matern kernel. And so it seems, and this is the part that's pretty open in the air, what in the world's going on, it seems that we've learned like a more expressive function class than the thing we trained it on. That seems a little unbelievable. It seems like somehow we're cheating, or maybe not. Maybe this is like, similar to what we see in other parts of the the deep learning world, double descent sort of, we perfectly fit the data and we are able to also go further. And so you can see that we really get some of this fine scale spatial variation. We're not smoothing it out. But more work to be done validating all this. Okay, so that concludes this part of the case study. I have a second case study if there's time, but I'm happy to take questions. Oh, here we go. Archive update coming soon. Oh, I already said this. So this is prior CVAE. Here are the other papers. Take a picture if you care. And recap. Right, so deep generative modeling. So this is not just for spatial stats. Maybe none of you care about that. This is not just for GPs. Hopefully some of you care about GPs. We can do this for lots of other things. And so what we've been playing with recently are ODEs. This is an SIR model, infectious disease, number infected here, and the actual ODE solution fit with, I don't know what, NumPy row stan is here in orange, and then our prior CVAE approach, again, the conditional version of it is in blue, and it's pretty good. It's not exactly the same, but pretty good. And here's this challenging double well ODE. I don't know so much about it, but it's not quite perfect. We're like over smoothing a little bit, but it's getting there, and we need to, I think, work on our loss functions a little bit, but this is very promising. Otherwise, you might have to do something very slow to fit these types of models. Okay, not in the simplest example, but suddenly the second that you make it more complicated, you have multiple populations, ages, mixing for an infectious disease model, and I don't know enough about DPs to know what makes these double well things more complicated, but it's easy to come up with totally intractable ODEs, SDEs, all these things. Okay. Ready for something completely different? Yeah, okay, cool. So this is a different case study. Remember, again, inferential artificial intelligence. So we are using AI and machine learning, and we are making decisions based on data. We are learning from data. So this is work with World Food Program. I helped found a network called the Machine Learning and Global Health Network. And I've dragged in basically everyone who's ever been involved with that network to help me with this project. So I put their logo there, but have a look at our website. Get in touch if you're interested in the things that we're doing. We do not currently have any North American collaborators. It's a Europe, Asia at the moment. Okay, so the World Food Program has a website called Hunger Map that they build based on surveys that they run in dozens of countries, plus some machine learning models that they run. And for any of the countries that are in their database, you can go and find out what is the food security situation in that country. This is Zimbabwe, and here are 10 provinces in Zimbabwe, think states in the United States. And there are a few problems with this. It's based on mobile phone data collection, so the data is not necessarily representative of the population, right? Because we're only reaching people who have mobile phones. And it's not necessarily actionable. If you're thinking about prioritizing food aid, you need to go down to the district level, a level of the hierarchy down from province, or even more local. So what can we do about that? So there are a few things that we are trying to do, that we are piloting. So one of those things is a statistical model, multi-level regression and post-stratification. And I'll tell you about it really quickly, but I think we're going to get to the active learning part sooner because I want to get your feedback on that. So multi-level regression and post-stratification says, fit a model. It's a small area estimation model, so I'm showing you the adjacency matrix. Fit a model that uses the covariates that you have, sex of the head of the household, education level of the head of the household, how big the household is, what type of water, is it from an improved water source that's piped in, or are they going down to a stream to get water, which might be dirty? What type of sanitation facilities are there? We put all of that together into some sort of generalized linear model, and then we predict something that we care about. World Food Program cares about food consumption scores, this metric they've been working on and validating for years and years about how much nutritional content, how much food, how many calories, how many different types of food groups people are getting on a weekly basis. Okay, so that's the multi-level regression model. If you've heard of Mr. P, that's the MR, Mr. P. And here's the post-stratification part of it. We've fit a model that tells us what's the relationship between these variables and the outcome. That doesn't tell us at the local level or for any subpopulation what's their situation. For that, we need a population. And so it's called a post-stratification frame. Weird jargon from the old school spatial survey stats literature. It just means that we have some data set that tells us what are the demographics of the people who live in every district that we care about. So here's a household with a single adult, here's a household with a single adult, here's a household with 3 children, here's a household with 3 adults and 2 children. For each of those households, along with their covariates, we can make a prediction using the model, food consumption score, and then we can aggregate, and that gives us the average food consumption score for this district. And of course, it's a Bayesian model, so we get uncertainty. Okay, so there are some interesting data sets. There are ways that we validate this. This is what it looks like when we go from 10 provinces to 91 districts. Questions about ground truth here. One way that we could try to find out what's really going on is to improve the survey itself, to try to get data that is representative of more subpopulations and more smaller geographies. And so that's what I want to tell you about. So here is the plan, and it's really happening. It's October something. We're really in wave 1, collecting 750 samples as we speak. I'm not doing it, but there's a mobile phone call center in Zimbabwe, works with the company in the United States, and we have told them, please call from this long list of people, right? Because sometimes people don't pick up the phone. So that's the first wave. It's a stratified random sample. This is like block Monte Carlo, if you've heard of that. It's a way of getting an unbiased estimate, but reducing the variance that you would get if you were just using simple random sample, vanilla Monte Carlo. Okay, so that's the first step. We need to do that because we need to know something about who responds. That's like a key thing in survey statistics, is a non-response bias, possible bias. So that's just the first wave. The second 3 waves, we're going to use some active learning ideas that we've been working on. And so that's what I want to tell you about. Any questions before I tell you about active learning, about just the basic setup? What the heck is going on? Are we really collecting data right now? Okay.
I think there's a question here.
Oh, please.
How do you actually do this stratification of a random sample?
Okay, so we have covariates. That's a key thing that is only possible because we are using the survey that the World Food Program has already been collecting. They've got, at this point, 20,000 respondents. We know the covariates: age, sex, education. Stratification means that we take a list of what we want to stratify on state in the US. So for loop, I equals 1 to 50, for each state, draw a random sample. And that's a stratified random sample. That's all it means.
So it's from a subpopulation
we already know the variables that we want to stratify based on, yeah. And if you already know them and you can do that in a very fine-grained way, maybe you don't need any of this. Like, that's one way to think about what's happening here, is that we're going to try to automatically decide what are the important variables to make sure we have sufficient samples of. So sometimes you'll read about a survey and it will say, the survey oversampled minority group X. That was to ensure representativeness for that minority group. And if they're a minority group, they're less than the majority. If they're 10% of the overall population, you have a sample of size 1,000, we might only have 100 of them. We can't say that much with that much precision. But if we oversample, if we say we're going to do 50% majority group, 50% minority group, then we should have good power in both groups. Okay, other questions? Okay, so there's been some previous work. There's been a lot of work in the experimental design literature, much less in survey design. And what it has tried to do is just get something like better response rates. So you might try to decide we're going to incentivize people. You might decide you're going to recontact people or do something to ensure that the people who you have randomly polled do really respond. And that is not what we're talking about. We're talking about changing the sample itself. And so we are going to build on the active learning and Bayesian optimization literature. So to remind you, if you haven't seen this in a while, if you've never seen it, this is a very fun part of the machine learning literature. This is from a great survey from Burr-Settles from 2010. This is the true data. We have a two-class classification problem, and if everything were labeled, this would be the true data, and we would use a linear decision boundary, and we'd do a fine job. But we don't have any labels on day 0. And so we need to decide how we're going to acquire labels. We're going to pay. We ourselves are going to label things. We're going to go to Amazon and Mechanical Turk, whatever it is. So we could just do that randomly. We could get 30 random samples, random sampling. If we do that, we end up with a decision boundary here, which is okay, but it's not great. Yeah, the decision boundary should be here. And, you know, by chance, it ends up here. If we use active learning, the classic active learning setup says, well, the very first step you pick randomly. The second or third or fourth step, when you've got a little bit of data, you sample where you're the most uncertain. And in a simple two-class classification with the decision boundary, that's as close as possible to the decision boundary. And so you can see that we have immediately started collecting up data points that are close to the eventual decision boundary. And so with n equals 30, we have a much better classifier. Yeah? So that's active learning. What about Bayesian optimization? Well, I'll just show you the picture, and you'll remember it if you've never seen it. So the true surface we're trying to maximize is in red, and we have one data point in this red data point here with, well, a little bit of jitter, and we're going to use an acquisition function in order to decide where we should get more data. And as we acquire more data, the GP concentrates. It's a surrogate for the true function. 1 data point, 2 data points, 3 data points, 4 data points, 5 data points, and there we go. We have found the maximum. Yeah? So these are great ideas. They work really well in all sorts of settings. They're not going to work out of the box for us, because for us, we have very low response rates. Those response rates depend on covariates, and that is not something that anyone has ever thought of in the Bayesian optimization or active learning literature, as far as I'm aware. There are high costs for getting more data, and we can't go one data point at a time. We need to give this call center in Zimbabwe a list to call from, so we need to plan ahead. And it's a survey, and usually surveys have like 20 or 30 questions. We don't just care about one thing we're trying to maximize. So here is what we do. We first, as you heard, collect data in order to estimate a response rate model, probability that someone will respond given their covariates. And we just use usually like a logistic regression for that, but you could use a neural network. And then here is the really new thing. People have done this, although it's not clear anyone's written it up, but commercial pollsters in the biz do this. The new thing is that we have this measure called the design effect. The measure that's called the design effect is the coefficient of variation of the weights. And survey weights are this weird dark art that people in the biz do, where they try to take the sample that they get, and then they say, you know, we should not just take a straight up mean of this. Let's take a weighted mean in order that whatever happened. We have too many men versus women, let's downweight the men. We have too many of the majority ethnic group, let's downweight that. And so those weights come from some process, and we don't want to do that much weighting, because if we have to do a lot of weighting, it means that we're adjusting for a lot of things, and we don't know that we're doing a good job. The perfect sample would have all of the weights equal 1. So we're going to try to minimize the design effect. And what's very cool is that we have a way of saying, if we are going to go try and contact these people, and we do in fact get the responses based on the response rate model, but in expectation we get responses, having acquired those people with their demographics, doesn't matter what the response is, but with their demographics, then suddenly the design effect is something. It's high, it's low, whatever it is. And we're going to use gradient descent to choose the people that we acquire, that we try to contact, in order to minimize that design effect. And so we've got some simulations, which I will not go into, that show that some various approaches kind of work. It's a little up in the air which of these approaches we're going to use. And what does it mean that they work? So the absolute error goes down for all of the methods, but we're hoping that the absolute error will go down faster, meaning we can run the survey quicker or pay less, or pay the same but get a lot better, more representative responses that have lower error. So that's it. I have 1 minute left. Okay, so this was case study 5, just to remind you. So we took data that was already being collected and did a better job disaggregating it. And then we took these active learning ideas. What's the big goal here? Inferential artificial intelligence. In this case, the big goal was trying to reach these underserved subpopulations and subgeographies to understand what's going on in those places for those people in order to enable this humanitarian aid agency to target aid effectively. Okay, so here you go. You already saw this slide, but if you didn't get a chance, you can take a picture of it. There's 3 other case studies I didn't talk about. I think that this one, which is from work with a collaborator at Harvard, Xiaoli Meng, will be particularly interesting to all of you. But if you care about epidemiology, if you care about children and policy, numbers 1 and numbers 2, have a look. And we ran our first workshop on machine learning and global health in Kigali at iClear in May. And there's a picture from me and from my PhD student, Giovanni. And we had to do a PCR test and wear masks because these are golden monkeys and they can also get COVID and not allowed to give them COVID. So that's what's going on. Thanks so much.